Hi guys, for today's lesson we're going to be dealing with differentiation by first principles. So first up, what do I mean by this word differentiation? So differentiation is the process of finding the gradient of a function. This is particularly useful for nonlinear functions which don't have a constant gradient. So the idea is that these nonlinear functions have different gradients for different coordinates on its line, and the differentiation process allows you to be able to find the gradient for these different points, because it's not always going to be the same number. So differentiation kind of alleviates this problem of having difficulty finding the gradient for these equations. Next up, a limit. So a limit is mathematical notation that describes a pronumeral which approaches a specific value. So it's not equal to a value, a pronumeral, it approaches a value, i.e. the pronumeral practically equals the approach number, but not quite. So e.g., have a look at this sort of notation here. So lim means limit, the limit as x approaches 10, like x with an arrow towards 10, of 3x. So that x is practically equal to 10, but not quite. It's super close to 10, it approaches it, but it's not quite there. But we can practically treat that x as a 10. So it's 3 multiplied by 10, and that is 30. So the idea is that as x approaches 10, 3x approaches 30. That's kind of the idea of a limit. Differentiation by first principles. So the gradient of a nonlinear function at a particular x coordinate. So this sort of formula we've got down here will tell us the gradient for a function at a particular x coordinate, and the notation looks like this. So this is what I call the derivative, and that kind of comes from the word differentiate. The derivative of f of x of the function, so it's like f dash of x, is estimated using this formula. So we've got the derivative of f of x, or f dash of x, that is equal to this formula right here. So we've got the limit as h approaches 0, and we've got x plus h being substituted into the function, minus f of x of the function, so just the original function, and the difference between those is being divided by h. Now remember that you typically can't divide by 0, but because h only approaches 0, it's not quite 0, you are allowed to divide by it. So yeah, remember that this is what we call the derivative of f of x, or f dash of x. So e.g., so let our function f of x equal x squared plus 5. We want to find the derivative of f of x, or f dash of x. So the idea is we start with our formula that we're given. I just literally rewrote that formula. Now substitute x plus h into our function. So our x is going to change to x plus h. So instead of x squared, it's going to be x plus h squared, and the plus 5 has to come too because it's part of the function. And then we're minusing the normal f of x, which is, we're just minusing this function here, and that's dividing by h, and we've still got our limit notation there. Now to simplify this numerator, we want to expand these brackets here. So expanding this perfect square, you get these three terms. The plus 5 comes down, and we're minusing x squared, and then we're minusing the plus 5, the minus and the plus 5. So we get that minus 5. Like terms can go together. So our plus 5 and minus 5 will cancel. Your x squared and your x squared will cancel, and you're left with 2xh plus h squared divided by h. When we get to this stage, you want to be able to cancel your h's. This is typically always going to happen, otherwise you've most likely done something wrong. So that h divided by that h, that will cancel, and this h and one of these h's will cancel. You're pretty much just dividing both of these terms by h, and that simplifies to 2x plus h, and that's going to be where we can almost stop. The idea is now we apply this limit. So the limit as h approaches 0, that means our h right here will become practically a 0, and we're going to be left with just 2 lots of x. So that is going to be our derivative. So our derivative is equal to 2 lots of x. So now we can use that to determine the gradient of this function at x equals minus 3. So because we figured out our derivative was 2x, this tells us the gradient at any point. We can change our x to a minus 3. That's what we want, where we want to find the gradient. And the derivative of our function at negative 3 is going to be equal to 2 lots of that number. So that's 2 lots of negative 3. Our gradient is going to be negative 6. You can see here from this derivative of 2x that whatever our x is, we can literally double it, and that will get us our gradient. So say if I put in a 10, that means our gradient would be 20. It's pretty much going to be 2 lots of that x coordinate. Hope this helps. Oh, we've got some more stuff, plenty more. So next up, we've got a tangent. What do I mean by a tangent? So a tangent is a straight line which just touches a curve. So the idea is, if we look really carefully at this graph here, I've got this curve like this. If I draw this line which practically just touches the curve, so it just touches the curve at this point. A tangent literally just grazes the curve. It'll just touch it at one point. It won't hit it twice. So that's what we call a tangent. And it's a tangent at x equals 1, because you can see here that our x value here is 1, and if I go straight to the line, that's the point where the tangent touches. So that's why it's a tangent at x equals 1. I can see here from this, like I'm using this tangent line to figure out a rise and a run. So the idea is pretty much, if you want to figure out the gradient at this point right here, you have to think to yourself, well, let's draw a tangent line, and then using that tangent line, we can make a rise and run from that, and we can find the gradient from the rise divided by run. So like you'll notice that like with these tangent lines, if I made a tangent at this point or this point or this point, the tangent line would look different. It would have a different gradient. So so you got to note, as I say down here, you got to note that the gradient of a nonlinear function differs throughout the curve. The gradient of the curve at x equals 1 is equal to the gradient of the tangent line. So that's pretty much the definition of the tangent of these sorts of curves. These gradients are constantly changing. Like here, if I use, say, this point right here, that's a negative gradient, but over here it's positive. It's always changing. So you got to think to yourself, what would be the gradient of my tangent line at these specific points? And that will tell you the correct gradient. But that's why we're doing this thing called differentiation, because this makes this process of finding gradients, like here, -6, so much easier. Like if I go to Desmos, so like for example, if you look at this curve which you see here, you can see that there's this tangent line at different points, and if I move the point, the tangent line moves as well. So you can see here at this point right here, the gradient would be positive. It's uphill. If I go all the way up to here, the tangent line would be the gradient would be roughly 0. It's a flat line, horizontal. If I go to here, the gradient would be negative. You can see that the gradients are changing as I move along this curve. It's going like, that's negative to positive to negative to positive, etc. And for all these different values of x, you need to be able to figure out exactly what the gradient of this tangent line is. Okay, continuing on. So let's do some example questions. So find the gradient of the tangent to the curve y equals 4x squared plus 3x at the point -2, 10 using first principles. So the idea is I give you a function, you need to tell me the gradient at this point on the function. Okay, and we're going to use the first principles formula to help us out. So I've used the formula. I want to know the gradient when x is equal to -2, so I change my x to a -2. I change all my x's in my formula to -2, and I want to figure out what this is equal to. So the idea is we need to put this into our function, and our function is right here. So that equals something like this. our x in our 4x squared changes to minus 2 plus h. And same thing here, 3 lots of that x, so our x changes to minus 2 plus h. Similar, we're taking away this function here, so we're minusing our x changing to a negative 2. So 4 lots of negative 2 squared plus 3 lots of negative 2, and that's all being divided by h. We can expand this bracket here to give you that, and that's all being multiplied by this 4, remember? That bracket expands to that, and this bracket here simplifies to 4 lots of 4 minus 6. I expand this bracket again to get all this stuff here. This bracket can expand to give minus 16 plus 6. And then finally, like terms here can simplify. So our 16s will cancel. Our minus 6 and plus 6 will cancel. You're typically going to see lots of things cancelling. Minus 16h and plus 3h, that gives us minus 13h. And our 4h squared comes down as well. This h is going to cancel with one of those h's, and minus 13h, that h and that h are going to cancel as well. That gives us a final expression of 4h minus 13. The limit as h approaches 0, that means 4 lots of h is 4 lots of 0. So that's going to leave us with this minus 13. So that means the gradient of the tangent at this point, negative 2 or negative 210, is going to be a gradient of negative 13. It's going to be a very steep downhill line. Hope this helps with the questions. Good luck.